All right, so this is Physics 106, Chapter 23, circuits. So last chapter really was in preparation for this chapter. So learning objectives: draw and interpret basic circuit diagrams, understand and analyze circuits containing resistors in series and parallel, understand the physical basis for Kirchhoff's laws, and use these laws to analyze circuits, understand the time-varying voltage and current in RC circuits, resistor-capacitor circuits. And I'm sorry, we're not going to do this last part. Now, before we get into it, I want to show you an email I received a number of years ago from a former student. He wrote this when he was in medical school. We won't read the whole thing. Aloha, Dr. Weber. It's Sunny from your BYUH physics classes. So I am about halfway through my first year of medical school, and I've been thinking about your classes a lot. Don't ever let pre-med kids trick themselves into thinking that physics isn't important as a doctor. We have recently been studying heart and lung physiology, and the models we use for blood and airflow are exactly the same as the models used for electric circuits. We use Ohm's law every day. Other cool ways physics keeps popping up is the model we use to discuss blood flow. We use circuit diagrams. So basically what he's saying is what you learned last chapter and this chapter they use in medical school a lot. And here's an update. So this guy, Sonny, he finished medical school and he's now working as an emergency room doctor in Massachusetts. Okay, so keep that in the back of your head when you're wondering why are you doing these crazy things. All right, let's review first. So we're talking about wires and resistors. So again, this is Ohm's law. The change in voltage along a wire equals the current times the resistance. The resistance is the resistivity, which depends on the material, the length of the wire, the cross-sectional area. And remember, this is constant for a given wire. All right, so let's use this. So let's say we have an ideal battery. What's an ideal battery? And let's say it's a 9-volt battery. Ideal battery means resistance is 0. We'll talk about a real battery later. So ideal battery has no resistance. And we're going to say we have an ideal wire, or a superconducting wire, with no resistance. All right, so obviously, this battery is providing an EMF, or a potential, correct? And so where does it go? Across the wire. So we have delta V wire equals delta V battery, because there's nothing else in this circuit, right? All right, so let's use Ohm's law. So delta V equals IR. And let's solve for the current. So I equals delta V over R. Okay, now let's see. Delta V battery is 9 volts. Okay, what's R? 0, right? 0. So what's 9 divided by 0? Infinity. All right. So that means the current is infinite, which means it's incredibly large. That's really horrible because it's really, really dangerous. It's dangerous for the human being, and it will melt the wire, okay? So this is not a good situation. We do not want this because we don't like dealing with really large currents because they're dangerous and they melt wires. So what we have to do then, we have to figure out a way to limit the current. So it's simple. You just add a resistor. Ta-da! All right? So we just add a resistor. So I just said 5K, so 5 kilo ohms. And there's nothing, I just picked that out of the top of my head, all right? And again, what's a resistor? It's just you can think of it as a wire with really, really bad conductivity, or a lot of resistivity, whatever you want to call it. All right? So we add a 5K resistor. So now, look, life is good now. So now we have delta V over R, so it's 5K, 5 times 10 to the third ohms. So now we have 9 volts divided by 5 times 10 to the third. That comes out to be 1.8 milliamps. And that's a safe current. All right? So basically, that's why resistors are important, to limit the current in a circuit. All right. There you go. And I showed you a picture of resistors in the previous chapter. Okay, so here's a question for you, a very important question. So charge flows through a light bulb. This is a light bulb. Okay. All right, so we have charge flowing through a light bulb. Then suppose all of a sudden somebody connects a wire from here to here. And it's an ideal wire, right? So the wire has no resistance. When the wire is connected, what's going to happen? So please pause your video and figure it out. And again, this is an important one, so think carefully. All right. So I like to think of these things, just pretend that you're the electron or the positive charge carrier. Now, a light bulb has resistance, right? So think if you're a positive charge carrier. You're moving along the wire here, and then you have a choice. You can go through here where there's resistance. You can go through here where there's no resistance. What are you going to do? Well, I mean, most normal positive charge carriers or people would take the path of least resistance, right? And that's exactly what happens. So the answer is 3. Because again, 0 resistance, a lot of resistance. All of the charge will travel along the path of 0 resistance. Okay, make sure you understand that. Okay, let's review Kirchhoff's rules. We saw this in the last chapter. At every junction, the sum of the currents in equals the sum of the currents out. That's just current conservation. We also had the loops, the sum of the voltage around the loop, any loop you want, as long as the starting point and the ending point is the same. That's what we mean by loop. So the sum of the voltages is 0. This is related to conservation of charge. This is related to conservation of energy. Okay, so what we're going to do is we have to analyze circuits, as our friend Sonny, who was in medical school, suggested. All right, it's important. Okay, so here we go. So this is what you have to do to analyze a circuit. Okay, using Kirchhoff's loop law, or loop rule, whatever. Number 1, draw the circuit diagram. Label all known and unknown quantities. Now, usually that's done for you, for a homework or an exam or something like that. 2, this is a really interesting one. Assign a direction to the current. Draw and label a current arrow I to show your choice. Now, here's what's cool about this. If you know the actual current direction, choose that direction. If you don't know the actual current direction, make an arbitrary choice. All that will happen if you choose wrong is that your value of I will end up negative. Okay? So that's the important thing. Just choose a direction of I. Don't worry about it. If it shows the wrong direction, it's going to be negative. So what? I mean, what we really care about is the magnitude. Okay, that's the first part. Oh boy, here we go. Next. This is the hard part, right? Travel around the loop. Start at any point, then go all the way around the loop in the direction you assigned to the current. That's the crucial point, right? When you travel around the loop, you want to do it in the same direction as you chose your current. Makes life easy that way. As you go through each circuit element, delta V is interpreted to mean delta V is the voltage downstream minus the voltage upstream. What's that mean? Okay, here. For an ideal battery in the negative to positive direction, see we're going here, right? Delta V battery is positive. It kind of makes sense. Let me think about it. Here it's negative, here it's positive. So what's the change in potential? Well, we go from negative to positive. It's plus, right? We gain potential. Okay, so delta V battery is plus. For an ideal battery in the positive to negative, it's minus, right? Because if you're going this way and you go from a plus to a minus, you lost potential. So it's minus. Okay, that kind of makes sense, you know. For a resistor, remember, a resistor dissipates energy or dissipates voltage, however you want to look at it. So it's always going to be minus IR, okay? You're always losing potential. And then you just apply the loop rule, right? The sum of the voltages is 0. So that's how to do it. We could do some examples. Let's do an example. By the way, I guarantee you'll have to do this on an exam. You'll have to do this in homework. And you'll also have to do this in lab. And if you want to go to medical school, you better know how to do it there too, right? Before you get to there. So it's important. Okay, so this is an easy one. This is only, I call this a one looper, all right? So this has a one loop. Later on, we'll do two loop. Those are more complicated. This is super easy. So let's do it. All right, so the first step was draw it. So we've already drawn it, right? Second step, you assign a direction to the current. Now, okay, so look at this is 15 volts. And remember, it goes away. Conventional current goes away from the plus, so that would go this way. This is 9 volts, so it would go this way. So which is going to be the bigger one? The current from the 15 or the current from the 9? Well, obviously this one. So we know the real current is going to be going clockwise. However, just to show you it doesn't matter, I'm going to do it counterclockwise, all right? Just for fun, because it doesn't matter. It's not even worth thinking about. Just assign a direction. Just choose a direction. You don't care. All right. Now what we want to do is we want to travel around the loop. And again, it doesn't matter where you start. I mean, just who cares? So I just like to start at a battery. No really good reason. So I'm going to start here. Okay, I don't have to. I just feel like it. All right, so start there. Okay, and remember, we want to go around the loop in the direction that we chose our current. So we're saying the current goes counterclockwise. So we're going to go around the loop counterclockwise. And if you do that, everything works out easily. So we start here. So from here to here, I gain 9 volts, right? Okay, now you know how I always harp about writing your units when you solve a physics problem? Well, this is one of these situations where forget about that. Don't bother with the units. Okay, so here to here we have plus 9. A plus 9. You don't have to write the plus, right? Okay, it's 9. And then, all right, you lose voltage as you go through resistor. Now remember, delta V equals IR. So what's the voltage loss? Well, it's I, which is I, that's what I'm trying to solve for, times R, which is 4. Okay? So it's minus 4I, right? The voltage is I, which we're trying to find, times the resistance, which is 4 ohms. And we're losing voltage because we're going in the same direction as the current, so it's minus 4I. Then we go along here. Okay, now look here. Here we're going from a plus to a minus, right? So we're losing 15 volts. So we have minus 15, all right? Then we go here, and we lose, again, V equals IR. So I times R, which is 2I. Minus 2I equals 0. So you see, you know, for the resistors, we have to use Ohm's law, right? Because the voltage is the current times the resistance. So Ohm's law is like fundamental. Okay, now let's do this. So let's see, 9 minus 15 is minus 6. Minus 4 minus 2 is minus 6. So we have minus 6 minus 6I equals 0. So minus 6 equals 6I. Divide by 6, negative 1 equals I. Ta-da! Okay, so what does that mean? It means that we chose the wrong direction. Well, we already knew that, right? I set it up to do that just for fun. Okay, so the real direction of the current is that way. Okay, but again, you don't have to sweat it. If you get a negative, you know you chose the wrong direction. Who cares? All right, now let's do some other things just to kind of check things. So what is delta V across the 4 ohm? Across the 4 ohm. the 4 ohm resistor. What is that? Well, delta V equals IR, right? So I is 1 amp, right? Because the magnitude, right? 1 amp. So we have 1 amp and 4 ohms. So that's 4 volts, okay? Delta V across the 2 ohm resistor. The delta V equals I, R, and that equals 2 volts, right? Okay, so let's see. Let's start here. Because remember, delta V is supposed to be 0. Let's see if it works, okay? So here, from here to here, you gain 15. So 15. And then here, you lost 4. Here, I'll put the volts. So minus 4 volts. Here, plus the minus, you lost 9. So minus 9 volts. So 4. Here, you lost 2 volts, right? So what does that equal? 15, what is that? 0, right? So in other words, the sum of the voltages, that's what we just figured out. The sum of the voltages, 15 minus 4 minus 9 minus 2, and that equals 0. So the loop rule works. All right, great. Again, this is an easy one. We'll do a more difficult one later. And you're not going to have one like this on a test. You're going to have a more difficult one. Okay. I don't know what's the deal with this. Anyway, this is supposed to be a delta. All right, so what is delta V across the unspecified circuit element? Does the potential increase or decrease when traveling through this element in the direction assigned to I? All right, so I is going clockwise. So you're going to figure out the magnitude and the sign. Right, so pause your video and figure this out, please, using the Kirchhoff loop rule. Okay, so let's see. Start anywhere, right? Let's start here. So we lose 8. So we have, okay, the sum of the voltages has to be 0, right? So let's just start here for no good reason. So we have minus 8. Then we have minus 6. Then we have plus 12. And then we have, I'll say x, all right, plus x. And that has to be 0. So what is that? 8 and 6 is 14. So we have minus 14 volts plus 12 volts plus x. So what does x have to be? X has to be what? 2 volts, right? And it has to be positive 2 volts, right? It has to be an increase. Agree? Because we have minus 14 plus 12. This has to be plus 2. So increase. Okay, now we're going to talk about connecting components in series and in parallel. We're going to do this with resistors and with capacitors. So you have to understand it. And what's funny about it is the laws for series is exactly opposite to the laws for capacitors. So don't get them mixed up. All right. Okay, so this is called connecting something in series. So here's resistor 1, here's resistor 2. What is the same for both resistors? So, you know, you have a single wire, right? And so what's the same for both resistors? Well, it's the current, right? The current comes in here, goes through here, comes in here, goes to there, comes in there, right? Remember, current is conserved. There's no other branches for the current to go, so the current is the same for both resistors. That's the key, all right? So I'm going to actually show you how to come up with these equations. I'm not going to just give them to you because that's sort of useless, all right? So what we want to do is we want to consider from point A to point B. And we're going to use Ohm's law a lot, so I'm going to write it up here. Remember how I said Ohm's law is like F equals MA? It really is. All right, so let's see. So the total voltage from A to B is just delta, here I'll go like this, V1 plus delta V2, okay? Okay, that's cool. Makes sense, right? But now I'm going to use Ohm's law, so that's I R1 plus I R2. So notice I didn't have to subscript the I because it's the same, right? The current is the same. Okay, well I can, take out an I, right? Just factor out the I. Now here's the thing, look it. Ohm's law says that voltage equals current times resistance. So here I have a voltage. Here I have a current. So in here I have a resistance, right? So basically, this thing here, that's what we're going to call the equivalent resistance, right? It has to be resistance. I mean, it is. It's R1 plus R2. So that's the equivalent resistance. So what am I saying? Just look at it. The equivalent resistance is just, for this case, just R1 plus R2, Well, what if I had like 1,000,000 resistors? Then the equivalent resistance would just be the sum of all of them. Okay? So that's the rule. I mean, pretty simple, The series rule is totally awesome. So in other words, I could replace this with this, okay? So in other words, I could just replace the 2 just with a 1. Now, why do you care? I mean, why do you do this? Well, they don't make resistors with any value. They just make resistors with certain values. So, like, I'm just going to make something up. So let's say you needed a 5 ohm resistor, but they don't make it. But let's say they make a 1 and a 4. Well, since they don't make a 5, but they make a 1 and a 4, you're going to you have 1 ohm and a 4 ohm, right? I mean, that's kind of like why it works, all right? Okay, so the series resistors is the simplest one of all. You just add them. Wonderful. Totally cool. Now, the challenging one at first is parallel. Okay, so this is called parallel. So you have a current coming in, then it splits, and we don't know how it splits, Like if this was a gigantic resistor, this was a tiny resistor, most of the current would go through here, hardly any would go through here. So we don't know, all right? So all we know is this is I1, this is I2, but we don't know which one is what. We don't know which one is bigger or small. We don't know anything right now, right? And then current goes through, then it adds and goes out. And of course, this is the same as that, right? So these are called parallel because they're parallel, All right, they're parallel. Okay, now look at that circuit diagram. Oops, I shouldn't have done that. And ask yourself, with a series, we have the current was the same for each resistor. But now, there's no way. I mean, it could, but, most likely it's not. So we don't know, we can't say that this current equals that current. But what is the same? What is the same for this guy and this guy? So think about it. I mean, there's not a whole lot of choices, right? I mean, here's Ohm's law. All right, so we know that the current's different. We know that the resistors are different. So what's probably the only thing that's the same? Probably the voltage, right? Well, let's prove it, okay? Let's just do the loop rule around this, okay? So just to show you something. So the sum of the voltages, according to Mr. Kirchhoff, is 0, right? So let's see. So let's start here, okay? So we go here. That's minus I1R1. And we go here. Okay, now look. This is the tricky part, which I want to avoid, right? You know, what we said earlier was when we go in the same direction as the current, it's always a minus IR, right? So we're going this way, we're going clockwise, and I1 goes this way, so the delta V is minus IR, minus I1R1. But now here, we're going this way, but the current is this way, so it's positive. Sorry about that. Plus I2R2. And that has to equal 0, right? Well, if this is true, that means that I1R1 equals I2R2, right? Well, that means delta V1 equals delta V2, okay? So that's basically it. So what I'm saying is when you have resistors in parallel, the voltages are the same, okay? The currents aren't the same, the resistances aren't the same, the voltages are the same. And we just proved it. All right, so the voltages are the same. That's the key, you know. With series, the current's the same. With parallel, the voltages are the same. Okay, so let's pick a junction. Any junction, doesn't really matter. Let's pick this junction, okay? All right, so what's true? What's true at that junction? What can we say? We have I coming in, I1 that way, I2 that way. What can we say? Conservation of current. We can say that I equals I1 plus I2. Let me look at I, whatever. That's I. Okay? Now, let's see. Solve for I using Ohm's law. So I equals delta V over R. Okay? So let's do it. So I1 is delta V over R1, right? The voltages are the same. I don't have to put a subscript there. I2 is delta V over R2. Now, I can pull out the delta V's. Then I have 1 over R1 plus 1 over R2. Okay, now, look at this equation. Current equals voltage divided by resistance, right? Current equals voltage divided by resistance. So what does this thing have to be? It has, all right, what does it have to be? It has to be 1 over the resistance, right? Right? I equals delta V divided by R. So this thing has to be 1 over R. Okay? So that's the rule. People don't like it because it's kind of weird, but what are you going to do, you know? All right, so here, this is what I'm saying. So 1 over R equivalent is 1 over R1 plus 1 over R2, on and on and on. Depends how many resistors you have. So if you wanted to, you could write it like this. You could say 1 over R equivalent equals the sum of 1 over R. Okay, that's one way to write it. That's fine. Some people don't like that, all right? Some people, because they don't like working with 1 over things, all right? So this is a different way to write it. So, you know, if you have A over B equals C over D, then you can flip both sides. So you can have B over A equals D over C, right? That's just good old, that's just algebra, you know, just flip both sides. So let's do that. Let's look at this and flip both sides. So then we're going to have R equivalent equals the sum over I, 1 over R, to the negative 1. Oops. Okay? So, you know, whatever you like. You can do that one or you can do that one. It's the same thing. So in other words, what I'm saying is we could replace this with a single resistor as long as that single resistor had this value. Okay? So again, here's the, you can use this one, right? This one, or you can use this one, whatever you like. If you use this one, you just got to remember this is 1 over R. So, you know, at the end you got to flip it because you want to get R, you know. So whatever you like, it works, you know. Okay, so here's your chance to see if you know how to use these equations. All right, here's a bunch of resistors. This is a circuit diagram, right? Here's your battery. I don't care about the volts because we just want to find the equivalent resistance, right? We want to find the equivalent resistance. So the first thing you have to do is ask yourself, well, is this series or parallel? Well, it's obviously not series because the same current's not going through each resistor, and these are in parallel, so we know it's parallel, right? Okay, so whatever you do, don't just ignore this and have me do it. You do it with your, get your calculator and you figure this out, please. So use this formula and figure out what it is. So pause your video and figure it out. All right, I assume you've done this. I sure hope so. Okay, so I'll show you how to do it. So I'll do it. Okay, I'm going to do it this one. So 1 over R equivalent equals 1 over 10 plus 1 over 20 plus, hey, we can do this we don't need a calculator, right? This is awesome. So we want to get common denominators. So multiply this by 2 over 2. This becomes a 2. This becomes a 20. Same thing here. Multiply top and bottom by 2 over 2, right? So this becomes a 2. This becomes a 20. So we have 2 plus 1 plus 2 is 5. So we have 5 over 20 ohms. So this is a good, if you write, here you really should write your units because it'll help you not make a silly mistake. So we have 1 over R equivalent equals, oh, by the way, what's 5 over 20? It's 1/4, right? Right? Divide by 5, divide by 5. Okay, so we have 1 over R equivalent equals 1 over 4 ohms. So they flip both sides, or just look at the silly thing, and therefore R equivalent equals 4 ohms. So that's how you do it, okay? Now, there's something interesting in this. Look, we had a 20 ohm and a 10 ohm and a 20 ohm and a 10 ohm, right? And so, if these guys were connected in series, it'd be 40, correct? It'd be 40 ohms, but they're connected in parallel. So what's the equivalent? It's 4. So what does that mean? When you add resistors in parallel, does the resistance increase or decrease? Well, it decreases, okay? So when you add the resistors in series, the total resistance increases. When you add resistors in parallel, the total resistance decreases. And you'll see that in lab. All right. Let's quit.